Okay, today we're going to cover tests involving proportions. And we're going to do the one proportion z-test. So we'll be back to the z-table now. And we're going to do the two proportion z-test, which of course will also use the z-table. And first of all, I want to talk about what's the same as what we've been doing. Okay. We're still going to have an HO and an HA. HO is still going to have an equal sign in it. It just might be something like population proportion greater than 0.3, or for two proportions it might be PA equal to PB. But it's always going to have an equal sign in it. And your alternative is going to be whatever, this is what the problem is asking. The research question, whatever's being asked in the test. So it might say, I'm sorry, I wrote that, I said it right. That should be an equal sign right there, sorry. So it might ask, for example, is the population proportion greater than 0.3? Of course, it could say less. Or it might ask in a two proportion, can we conclude that there is a difference between the two proportions? So the main thing I want to get at is, the main idea hasn't changed. It's just that now we have a categorical variable. Like each one of these is going to be, like this might be the proportion who answered yes greater than 3. And this one might be referring to the proportion of males that said yes versus the proportion of females that said yes. So you have two groups, and we're looking at proportions within each one of them. We're still going to have decision rules, right? Like reject HO, if z-test, let's say greater than, I'm making up the number here, 1.645. If it was a one-tailed test in 05, that's what it would be. We're still going to have a test statistic, z-test, and it's going to equal the statistic minus the hypothesized parameter over the standard error. So for one proportion, that might be p hat, well it would be p hat, minus the hypothesized proportion over the standard error, which I'll go ahead and give you the formula. You will have a formula sheet that has this on it. The formulas that I passed out today and that are also available on Blackboard, you will have those formula sheets as well as the Z and T tables available during the test. I'll go ahead and give you the standard error for this one. It's the square root of pH QH over N, where QH is just 1 minus pH. They're complements and they have to add to 1. So you could think of, if the proportion yes is 0.3, the proportion no would be 0.7. If one of them's 0.2, the other one's 0.8. They have to add to 1. For the two sample proportion test, the statistic is p hat A minus p hat B minus the hypothesized difference, which, like the two sample t-test, this is always going to be 0. Again, it could be something different than that, but we will only do the case of simple differences, so we'll use 0 for that. And the standard error for that is going to be P bar Q bar 1 over NA plus 1 over NB. When we get to working some problems, I'll say a little bit more about that, but that's just the average proportion, weighted average, across both groups. Okay? That'll make more sense when we have a specific example, but I just want to get the formulas and things out there right now. But again, both of these are statistic minus hypothesized parameter over standard error. So, in fact, all the problems that we've been doing, whether it's the t-test for one sample, the matched pairs test, again for one sample, but you're looking at the differences. The difference between two sample means for independent groups, proportions or difference between proportions, they all follow that pattern when they have when you're computing a test statistic. Similarly, when we do confidence intervals, those are all the statistic plus or minus a confidence coefficient, which is going to be a z or a t. In these problems, it's going to be z, times standard error. One thing I want to go ahead and say right away is that with proportions, both the 1 and the 2 proportion z-test, the standard errors are calculated slightly differently for confidence intervals than they are for hypothesis tests. So when we get to the confidence interval for 1, it's going to be p hat, the statistic, plus or minus z, and it's going to be p hat q hat over n. So notice up here we used hypothesized proportion, so we'll get our proportion from the hypothesis itself. If it were this problem, it would be 0.3 and 0.7. And if HO is true, that's the best estimate, based on the proportion that's consistent with the null hypothesis, which is assumed to be true for the analysis. But with the confidence interval, you don't have to have a hypothesis for that. Therefore, instead of using some hypothesized proportion, you would use the sample proportion. So let's say that we took a sample of 100 and 24 said yes. P hat would be 0.24, just 24 out of 100. So up here you would use the hypothesized 0.3, and here you would use the sample proportion that you collected from the data. And then for the 2 proportion, it's going to be p hat A minus p hat B, the statistic, plus or minus a z, times the standard error, which is going to be p hat A q hat A over NA, plus p hat B q hat B over NB. There's a similar logic. You make more sense when we get to specific numbers, but this is basically based on the null hypothesis. But again, with confidence intervals, all you have available to you is the data itself. Or it's all you have to have available. You don't even have to have a hypothesis at all when you do a confidence interval. And this is problem 1 on the sheet that I gave you. And so there's a claim that 60% of retirees have bought merchandise online using a credit card in the past month. That's the claim. And someone thinks that it's lower than that. There are no means and standard deviations. It's percentage or proportion. That should be the first clue. The other thing is, think about the variable. The variable is whether or not they used a credit card for an online purchase in the last month. They either did or they didn't. That's all the way back to exam 1. Do we have a categorical variable with proportions or a quantitative variable with means? This one is a categorical variable, and we have n is equal to 150, and x, just the number of yeses, was 84, and HO and HR, the claim was that the population proportion was less than 0.6, lower, and then this will be P equal to 0.6. So P hat is X over N, X just being the number of yeses, 84 divided by 150 is equal to 0.56. If we're doing a confidence interval, 90% confidence interval, we're going to have P hat plus or minus Z times the square root of P hat Q hat over N. So we'll have 0.56 plus or minus 1.645 for a 90% confidence interval. 0.56, 1 minus that is 0.44, and then the sample size was 150. And that comes out to be 0.493 to 0.627. You should also verify that using the stat function on your calculator, which is stat tests, go down to option A, which is 1 proportion Z interval. And after you do that, all you have to do is put in 84, 150 right here. If you put it in 150 and then 84, you're going to get an error message. So 84 over 150, give it the confidence level, and calculate. And I did both of those already. Did it both with the formula and then with the calculator, and that's the answer. So from that, can we conclude that the population proportion is less than 0.6? No, because the interval includes values that go as high as 0.627. So you have to again focus on the whole interval. So if we were using it to test this hypothesis, which we don't have to, we could just be using it to get an estimate. If we reported it like this, let me calculate here. If we reported this like this, 0.56 plus or minus, now I'm just going to multiply this part out, and I got 0.067. That's how you see things when you look at political polls. That could be, for example, the proportion that favor a particular candidate or position, plus or minus, and you've seen them say that, a margin of error. So in this case, we can't conclude that less than 60% favor the topic, the position or whatever, if it were that kind of problem. But that's what you see in the news quite frequently. Okay, this is going to get a little bit messy, full page, but I want to do that for a reason, because I want to highlight the differences between standard errors in particular. If we were, actually, I need to say something else first. This is a one-tailed test with 05. If you would look at the bottom of the second page on the T-table, you can see confidence level 90, and the Z values are in the bottom row. Okay, so instead of having to memorize those and write them on the board, that you can get all of your one-tailed test, well, two-tailed test, confidence level, it's all right there, and it's just this bottom row. Then you can, of course, see the 1.645 and the 1.96. Those should be at least slightly familiar by now. Then you got 2.326 and 2.576 for 98 and 99% confidence intervals. Okay. Just wanted to point that out, so you'll have that you'll have both the Z table and this, but when you're getting Z values for confidence intervals or hypothesis tests, you should just go to the bottom of the t-table. Reject HO if z-test is less than minus 1.645. That would be our decision rule. And our calculation of z-test would equal the statistic minus the hypothesized parameter divided by the square root of pH QH over N, or 0.56 minus 0.6 divided by the square root of 0.6, 1 minus that, which is 0.4, over 150. I'll calculate that in a minute, but right now what I want to highlight is that the standard errors are different for hypothesis testing and for confidence intervals. Again, when we're doing our hypothesis test, we are assuming HO was true. So we use the 0.6, the hypothesized proportion. With the confidence interval, we don't even have to have a hypothesis, so we have to use the sample proportion that we had and calculated from the data itself. And that comes out to be exactly minus 1. And minus 1 is not less than minus 1.645. Therefore, we will fail to reject HO, conclude that the population proportion might not be less than 60. So the consumer group shouldn't go saying it's less than 60. It could be 60, or it could be actually slightly lower. Of course, it could be lower. We went as low as 0.493 in our confidence interval, but we shouldn't. With probabilities, there is a chance, given our calculations and our level of significance, there's a chance that it's not less than 60. Okay, we can also get the p-value, and since it's a z-test, we can calculate that by hand and show all of our work and everything. We have a z-test equal to minus 1, and if you would look on your z-table, that goes with 3413, half of about 68. You've seen that on your z-table plenty of times. I don't happen to have one pulled up right now, but you can look on your z-table and verify that if you go to 1.0, you would have an area of 0.3413. And so when we draw our sampling distribution, now we have a distribution of p-hats. That's the statistics that's being distributed. So we only have one sample, and we have a 0.56. If the population proportion was 0.6, then we might get a 0.56, we might get a 0.61, a 0.59, a 0.63. What we're saying is if we have a large enough sample size, this distribution will be a bell curve centered on the population parameter, which is 0.6, and we observed a specific value of p hat that's equal to 0.56, and we want to know the likelihood of observing a value that's 0.56 or below that extreme in the direction of the research hypothesis if HO is true. And so if this is 3413, then this is 0.1587. That's the p-value. So remember, we would reject HO if the p-value is less than whatever we have for a level of significance. 0.1587 is not less than 0.05. So we fail to reject HO they shouldn't claim that it's less than 0.6. Okay, there's one more issue I want to deal with right now, and that's the question of, is the sample size large enough? The first thing I have to tell you is that 15-40-100 rule does not apply when you're dealing with proportions. That's the rule when you have means. For one thing, for a proportion, you can't draw a box plot to see if there are outliers. So, or extreme values. That's not really the issue here. It's a different set of rules. And the rule for determining whether or not a sample size is large enough, sort of the central limit theorem in a different way, is large enough to guarantee that that sampling distribution we drew down here is a bell curve. So the rule is, are the numbers of yeses and nos both greater than 10? Yeses and nos both greater than 10. And I believe that I have that written on the formula sheet as well. So for the confidence interval, we would just use sample proportions, and remember we had X was 84. That's the number of yeses. That's greater than 10. So we're good on that one. But we also have to get the number of no's, which would be 150 minus 84 is 66. If out of 150, 84 said yes, then 66 must have said no. So for the confidence interval, 66 and 84 both greater than 10, the sample size is large enough. For the hypothesis test, it's really what we expect for yeses and nos. So we would have our expectation, if for yeses, would be 0.6 times 150, and for nos, 0.4 times 150. And I believe that's 90 and 60. So both of those are greater than 5. So we're good for our hypothesis testing as well. Hypothesis testing based on what you would expect if HO is true, 60% of your sample size and 40% of your sample size. Again, based on HO. Confidence intervals, data, hypothesis testing based on what you hypothesized. And I'll just go ahead and say that that is something that tends to be, I think, forgotten. We start with the 15-40-100 and we work for it for a while. Now to get to proportions, it's slightly different. And kind of went off on a little bit of tangent that we needed to be on. But we also have that conditional interpretation of the p-value, the if-then stuff. So the way for that conditional statement, it's always if HO is true. So in this case, if P is equal to 0.6, if the null hypothesis is true, then there is a p-value chance, 0.1587 chance. I'm going to say this in words, but on your graph, it's of getting what we have in the tail there. That's what we're looking at. We're saying if this is true, there's this chance of being from here down. So there's a 0.1587 or 15.87%, think of it that way, chance of obtaining a p-value. I'm sorry, down here at the bottom, a p-hat less than or equal to 0.56. And that's the statistic that we observed, and we're looking from there down, since it's a one-tailed lower test. Okay, again, this is just a shortened version of number 5 on your problem sheet. And in this case, we have 2 samples. Well, that's LOW. And it is on the problems that you have with you. I just typed this at the beginning of class because I didn't have the problem here. Well, anyway, there are two samples, 100 high-income voters and 75 low-income voters. And all we're asking each one of these, whether it's a high income or a low income, is do they support a decrease in the sales tax? So those are both yes, no. So what we have, let's say summary here, I'll call the high income group A. We have a sample size of 100. We have number of yes is 60. And we have P hat, I think I'll just write here, P hat A is equal to 0.6. That's just 60 out of 100. And for group B, we have 40 out of 75. Now that I think of it, it doesn't make any difference, but it might have been easier to put the X on top and then the N. P hat B is going to be 40 out of 75. And that's, I'm going to carry that out to 0.533. Make sure you leave some space right here. We'll need it when we get to the hypothesis test. For the confidence interval, we just have P hat A minus P hat B. Think of that as one number, the 0.6 minus the 0.533, or 0.067. That's just the same number. Plus or minus Z, sorry, I'll start up here, plus or minus Z times the standard error, P hat A, Q hat A, NA, plus P hat B, Q hat B over NB. So plus or minus for 98%, that's 2.326. 98% is right here. There's your 2.326. Just using the bottom of the t-table. 98%, 2.326. Times now the standard error. Let's see if I can get this all in here. 0.6. 1 minus that is 0.4. Divided by 100. Plus, now the 0.533. Well, that's 0.467. Divided by 75. Let me write all of that over a little bit more. 0.067 plus or minus 2.326. 0.6. That was our P hat A. 1 minus that. Proportion, yes. Proportion would be 0.4. 0.533. Now I'm wishing I only carried this out 2 places. But this will be a little more accurate, a little bit closer to what we would get with a calculator. So 5.33 yes, 1 minus that, or 467 no, and divide by the sample size for that. So I just calculated that. In a second I'm going to check with my stat function to make sure I didn't push something in wrong, but minus 0.109 about to about 0.243. Now I'm going to check that on my calculator, see if I made any button pushing errors or anything like that. So stat, test, to proportion Z interval, that's option A on your, option B on your calculator. So hit enter there. And so X1 was 60 out of 100. X2 was 40 out of 75. And we had 98 for the confidence interval. Minus 1093 to 0.243. Close enough. I still did a little bit of rounding with that 0.533. It would have been 0.533333. So the more you carry that out, the more accurate. But carrying out that 3 places, I got pretty darn close to what I would get with the calculator. To interpret that, if we just want to know if there's a difference between the two groups, which is likely, we would say that there might not be any difference between the two groups because the interval includes 0. So now we have 3 types of confidence intervals, which we interpret by looking to see whether or not the interval includes 0. The matched pairs t-test, the 2-sample t-test, and the 2-proportion z-test. Going back, for one proportion or for one mean, we just have to look at what's in our hypothesis, whatever we had for HO. And of course, really, HO, for all of those latter 3 cases, all has 0 in it if you state it as a difference. Or before I move to the hypothesis test, is the sample size large enough for this confidence interval? So we had 60 yeses in this first one, 60 yes, so 40 no. This is from our sample information, which is what we use for the confidence interval. And we had 40 yeses and 35 no's. That's just 75 minus 40. All of those greater than, did I say 5 or 10 on the other part? 10. 10. Let's put 10. And I'll tell you why I do that. Up until the last maybe 5 to 8 years, all the textbooks said 5. But they've become more conservative, and now almost all of the textbooks say 10. So I'm transitioning in my mind. I've been saying 5 for over 20 years. And then now all the books are saying 10. And so to be consistent with the books, so I don't have you reading one thing and then hearing me say something else, I'm trying to change my brain over, but it's pretty hard-coded in there, I have to admit. So 10, we'll use 10 for a cutoff. Okay, so now for the hypothesis test. If you look at that formula that I gave you, you'll see that there's a p-bar. Okay, p-bar. What that stands for is if we have a pooled proportion. I'm going to go here and say our HO is going to be PA equal to PB, or PA minus PB is equal to 0. So what that's saying is, if they're equal, it doesn't make any difference which group you're in. There's no distinction. We really just have one larger population if HO is true. So what that says is that we really have just a total of 175 people. It doesn't make any difference if they're high or low income. This is just saying it's one group. No reason to differentiate between them. They have the same proportions. And so we had 100 people that support the lower tax. And so our P-bar, I'll have to write this over here, is going to equal 100 divided by 75. I'm sorry, by 175. And that's, I'm going to round that to 0.57. You could round to 0.571 if you want. But that's P-bar, the pooled proportion. Now let's see, our HR was, we want to know if there's a difference So HR is PA not equal to PB. You could put PA minus PB not equal to 0. I think most people understand this better, equal or not equal to. But on HO I put this, so when I draw the sampling distribution, it reminds me that the center of the sampling distribution is 0. So now, with 0.01 as our alpha, over here, 0.01, first of all, let's start with, we have a two-tailed test. Okay, I wish I hadn't done this, but we will. It's going to be a different number now than we had in the other part. We have a two-tailed test, and we have 0, 1. So that's going to go with a z value of 2.576. Okay. Two-tailed test, 01, 2.576. If we were 0.02, then it would have been the same number as we had before. But let's go ahead and do it differently. Two-tailed test, 01, 2.576. It's a two-tailed test, so we're going to reject HO. If z-test is greater than 2.576 or less than minus 2.576. And with the two-tailed test, we can reject on either side. Our z-test is equal to the statistic p hat A minus p hat B minus the hypothesized proportion PA minus PB hypothesized over the standard error, which is the square root of P bar Q bar, that's a parenthesis there, 1 over NA plus 1 over NB. Our sample proportions, I think, all right, it's 0.6, doing this from memory, 0.533, I believe that's what we had. Minus the hypothesized difference, which is 0. Okay, again, that is always going to be 0. Divided by the square root 0.57, or 571 if you want to carry it out that far. 1 minus that is 0.43 times 1 over 100 plus 1 over 75. I'm getting 0.886. I want to check that now with my calculator. So I'm going to go to Stat, Tests, Two Proportion Z-Test, which is option 6. And I have 60 out of 100, 40 out of 75. Not equal to, it's a two-tailed test. And calculate. 0.882 I got here. Sorry, I actually did, this was 0.886 on my calculator, so that is correct. 0.886 is not greater than 2.576. 0.886 is not less than minus 2.576. So we fail to reject HO and conclude PA could equal PB. Might not be a difference in support for the lower sales tax for high and low income voters. Before I go on to graphing the sampling distribution and all of that, I want to go back to the sample size issue. So for the hypothesis test, we're using the pooled, not writing very well for me right now, but we're using the pooled, the 100, if I can. Awesome. Well, okay, it's not going to work for a second here. We're using the pooled value. We had 100 yeses in the whole thing and 75 no's in the whole thing. So for the hypothesis test, 100, both 100 and 75 are greater than 10. Therefore, we have a valid process. We are guaranteed a sampling distribution that's a bell curve. That board. And so I'm going to do the sampling distribution just on the full screen here. We've just said it's going to be a bell curve because both 100 and 75 are greater than 10. The distribution now is the difference between sample proportions. So you would take two samples. In this case, we had 60 out of 100 and 40 out of 75. We had a difference between those proportions. It was 0.067, the 0.6 minus 0.533. But the next time we take two samples of high and low income voters and look at the difference between proportions, we would get something else. And then again, we would get something else. And then again, we would get something else. What we do know is that the distribution of those differences between sample proportions will follow a bell curve. And if the sampling, if the null hypothesis is true, that this will be PA minus PB equal to 0. The difference that we observed was P hat A minus P hat B was equal to 0.6 minus 0.533 is equal to 0.067. So this point is at 0.067. And we looked up, when we calculated the Z, we found that that was about 0.89, 0.886 when I calculated it by hand. If you used the calculator, you would have gotten 0.88. So we'll have a slight difference there. Either one is fine. I'm going to go with 89, the one I computed by hand. And so this point is 0.89 standard errors above the mean. If you look in your Z table, I don't happen to have one with me today. If you guys would have one, if you could look up for 0.89 and give me the area for that. 3133. 3133. So that's from here to here. 0.3133. So this area will be 0.5. Let me shade this in for the p-value. 0.5 minus 0.3133. 0.1867, if my math's okay. I believe I'm good on that. You guys agree with your calculator there? Guess I can use mine. Yeah. Okay. that's not the p-value, because this was a two-tailed test. Okay, so we also have p-value over here, another 0.1867. So the total p-value is equal to twice 0.1867, and that's equal to 0.3734. And remember, right here, our difference is 0.067. That's this distance. And when we're looking at a two-tailed test, we go the same distance the other way. Since the center is 0, we just have to, let's give it the same number, but put a negative on it. So now we would say in our conditional statement, but let's do it first without the conditional. We had, what was the alpha level on here? 0.01. So we said we would reject if the p-value is less than 0.01. Well, 0.3764 is not less than 0.01, so we'd fail to reject HO, make the same conclusion we had on the other page, that there might not be a difference between population proportions, there might not be a difference between low and high income voters in terms of whether or not they support this sales tax and decrease. So if you're just interpreting in terms of the hypothesis, that's good. But if I ask you for the conditional statement, which is really what a p-value is, and the reason I say this is the p-value is based on HO being true. So if PA minus PB is equal to 0, if HO is true, of course you could have just put if PA is equal to PB. Neither of those is any more or less correct than the other, either one. Then there is a pretty large chance, a 0.3764 chance. In other words, if there's no difference, we'd get that far away from the center almost 38% of the time. We're certainly not going to reject any HO if we would get the opposite 38% of the time, or if we're within sampling error 38% of the time. Anyway, there's a p-value chance of, and with two-tailed tests, I usually put it this way: if one of the following is true, and again, I'm just reading what's on my graph here. Okay, it's up here or down here. If PA minus PB is greater than 0.067, or PA minus PB less than minus 0.067. So when we have a two-tailed test, you might think of it as we want to take note in either direction. If this is favored more by low income or favored more by low, either by low or high, a difference in either direction is something we're going to pay attention to. Let's say if you're a politician or something, you might pay attention to that. And I guess somewhat cynically, tailor your message differently to different groups if there is a difference. Probably a better example, to me, one of the best examples of a two-tailed test and why you would want to evaluate your p-values and things in this way is the feeling of, I told you, I used to work at this furniture factory. We made sofas and chairs and things like that. Our break room had this Coke machine. It cost 10 cents. And so in the Coke machine here, what would happen is you put in your dime, and then a cup would drop down. It held 6 ounces. And then some ice would spill down into the cup. And then some soda, Coke or Dr. Pepper or root beer, whatever you were drinking, would come in there. So when here's the cup, 6 ounces. When do we want to adjust the machine or pay attention to things? Well, if we get, let's say, too much, we pour in this much Coke, we want to take note of that because, now you're wasting Coke off the side of the cup. But we also want to pay attention, if it's just putting this much soda in there because, if me or Leon or Richard or any other people that were working in there only got half a cup of Coke when we put our dime in there, we were going to be angry. 10 cents, that's a lot of money. Well, it is when you're making $1.65 an hour. When your check for a 40-hour week is $61.26, 10 cents is meaningful, But anyway, the point is, with a two-tailed test, you're concerned with a difference in either direction. So anytime I get too high and there's a possibility that Coke's going to spill over, I want to pay attention, adjust the machine if I'm the person operating the machine. But I also want to pay attention if it's too much. So, here's my 6 ounces. At some point here, I'm going to expect some random variation. But at some point, there's too much, so I have p-value over here. And before I look at the machine, I don't make I'm not just concerned in one direction or the other, I'm concerned with both. So that's just sort of that's with a mean, but it's just an explanation or an idea of what the p-value and why you might want to have a two-tailed test.